polynomials, except we're going to talk about polynomial division. And there's two different ways that we're going to utilize polynomial division. I'm going to show you one way in which we can do it via long division. And then I'm going to show you synthetic division, which is a much easier use of our time, much more quick. When I'm looking at polynomial division, we can say that the d of x, which is our divisor, and the p of x, which is the dividend. And if you are in need of some vocabulary reminding, when looking at a particular example that we are already used to seeing with long division and values, the d of x, again, is the divisor. So I'll maybe put them over here with our example. And p of x, which is the dividend, are non-zero polynomials where the degree of p is greater than or equal to the degree of d. So the degree of our inside value has to be greater than or equal to the outside variable. There exists then two unique polynomials, the quotient polynomial, q of x, and the remainder polynomial, r of x. And it could be a polynomial or it could be a whole number as well. If we have a remainder of 0, then we know that it divides evenly, and it then is called a factor of p of x. We're going to talk more about that in a second. It divides evenly, and so therefore it is a factor. The remainder theorem states that we have a polynomial of degree at least 1, and c is a real number when we have the polynomial and it's divided by x minus that real number. The remainder can be found by substituting the real number into the polynomial, and we'll talk about that in a little while. The factor theorem states that if p is a polynomial, the real number c is a 0. Remember, 0 is the same as an x-intercept or a solution of p if and only if x minus c is in fact a factor of the polynomial itself. So that was a lot of blah, 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 right? Let's head over to slide 2 where we can look at some examples. I have x squared plus 6x plus 7, and let's see and divide by x minus 2 using long division. We want to make sure that our polynomials are written in descending order. So that the highest exponent is first and then every subsequent one after that. I'm going to have on the inside x squared plus 6x plus 7, and on the outside x minus 2. So a little bit of vocab. We have p of x is on the inside. We have d of x, the divisor, on the outside. So let's start by using long division. I have x. I want to make x squared from x. So to get from x to x squared, I need to multiply by x. I'm now going to take x from the top and multiply it by everything on the left. Well, x times x is x squared, and x times negative 2 is negative 2x. When we typically do long division, we then subtract, right? So I need to subtract this whole thing. I'm subtracting this whole piece. So I need to distribute my sign so that I have negative x squared and positive 2x when I distribute. What's left over then? Well, x squared minus x squareds are eliminated. They create a 0 pair. And 6x plus 2x is 8x. And then we bring down positive 7. And we start again. I have x. What do I need to multiply x by such that I get 8x? Well, x times positive 8 gives me 8x, and then multiply everything on the left. 8 times x is 8x, and 8 times -2 is -16. And then typically in long division, we want to subtract all of these items. So when I subtract, we need to distribute. We have -8x, +16, and then this disappears. 8x minus 8x creates a 0 pair, and 7 plus 16 is 23. 23 is the remainder polynomial. So we do have a remainder. Our remainder is +23, so we can rewrite x squared plus 6x plus 7 is equal to taking our divisor of x minus 2 times the quotient, so this was our quotient, x plus 8, and adding our remainder. So our polynomial was equal to the divisor times the quotient plus the remainder, kind of putting them all together. And since there is a remainder, there was a remainder of 23 here, we have a remainder. It doesn't go in evenly, therefore we can also say that x minus 2, what we are trying to divide since it didn't go in evenly, x minus 2 is not a factor because it has a remainder of 23. If it had a remainder of 0, it would be. Now let's take a look at how we can divide the same polynomial, but let's use synthetic division so that it can go much more quickly. Let's use synthetic division. It still has to be written in descending order, and I need to take my my divisor and set it equal to 0 and solve for x. We want to know, does x equal 2? That's our ultimate goal. Does x equal 2? I'm going to draw a vertical line. On the left is going to be the 2 that I found on when I set my divisor equal to 0. And on the right-hand side, I'm going to pull the coefficients from my polynomial. My coefficients are 1 from x squared, +6 from x, and 7, the constant. I'm always going to bring down my first digit, regardless if it's what number it is. Then I'm going to take 2 times that digit, and 2 times 1 is 2, and I bring that value up underneath 6 and add those values together. 6 plus 2 is 8, and I do the same. 2 times 8 is 16, and I bring that to the next location. 7 plus 16 is 23. This value is always the remainder. And then we work our way backwards. So we would have 0x as our constant, 1x if we had another one, x squared if we had another one, x cubed. These now become the coefficients in that order, working our way backwards. We have 1x plus 8 with a remainder of 23. Notice how much more efficient this is when we get to doing the synthetic division. There are a lot less room for error. But notice it tells us the exact same thing. It gave us the x plus 8, which was the quotient. It gave us the remainder, telling us the exact same things as the information in green below. giving us all that exact same information. Let's head to slide 3 and we'll look at another example. Let p of x be 2x cubed minus 5x squared plus 3. Find p of negative 2 using the remainder theorem. And check your answer by substitution. Use the fact that x equals 1 is a 0 and then find all of the real zeros. I know that I'm going to need to find possibly three solutions because the highest power I see is 3. So I know I'm going to need 3 solutions. What those are, we're not quite sure. They could be a combination of whole numbers, and it could be a combination of real and non-real, etc. We're going to talk more about that in detail as we go along with Unit 3. But let's first take a look at Part A. Use the remainder theorem and then check your answer by substitution. So I want to know, is negative 2 a solution? Is x equals negative 2 a solution? That's the question we're going to answer. I can use synthetic division to determine that. So negative 2, grabbing the coefficients from our polynomial written in descending order. I have 2, negative 5. Notice I have 0 x's. So I'm going to put 0 for x as my placeholder and 3 is my constant. Always bring down the first value. Then I take negative 2 times 2, which is negative 4, and bring that up top. Negative 5 minus 4 is negative 9, and repeat negative 2 times negative 9 is positive 18. Bring that under 0. 0 plus 18 is still 18. Negative 2 times 18 is negative 36. And 3 minus 36 is negative 33. Notice we have a remainder. We have a remainder, so negative 2 is not a solution. Notice also that when I substitute p of negative 2 into the polynomial that's given, so 2 times negative 2 cubed minus 5 times negative 2 squared plus 3, I end up with 2 times negative 8 minus 5 times 4 plus 3. So negative 16 minus 20 plus 3. Notice what happens. This is not a coincidence that when I substitute the value itself into the polynomial and I substitute the value of negative 2 and use synthetic division, that my remainder is the same. This is the exact remainder theorem we talked about on the front page. Directly correlated, not a coincidence. I also see that when I graph 2x cubed minus 5x squared into decimals, notice that negative 2 is not a solution. Okay, I'm going to erase some of these items here so that we can tackle Part B. Part B says, use the fact that x is 1 is a 0. Remember, is a 0, so it is a solution. So that we can find all the real zeros of p. Well, we can see that 1 is a solution. However, we have a couple of them that are also solutions, but they're kind of ugly decimals. They're not easily able to identify. So how can we use this to help us find what those exact solutions might be? We're going to reduce the polynomial. To do that, we're going to utilize synthetic division. Since I know 1 is a solution, I'm going to use 1 and synthetically divide out 1 from the polynomial 2x cubed minus 5x squared plus 0x plus 3. So 2, negative 5, 0, and 3, since I have 0 x's. Always bring down the first value. 1 times 2 is 2, so I bring that up here. Negative 5 plus 2 is negative 3. 1 times negative 3 is negative 3. 0 minus 3 is negative 3, and one more time. 1 times negative 3 is negative 3. Ooh, notice that we have a 0. Remainder of 0, because we obviously see that 1 is a solution. And now we have a reduced polynomial. So we have our coefficient, so 0x's, our coefficients of 0x, 1x, x squared, etc. We now have the two items, x minus 1. Since right now we know x equals 1 is a solution, so x minus 1 is the polynomial. And we have 2x squareds minus 3x minus 3. This 2x squared minus 3x minus 3 is called the reduced polynomial. It was also the quotient and x minus 1 was the divisor. We have no remainder, so we don't need to add a remainder to this. But how can we utilize then 2x squared minus 3x minus 3? How are we going to be able to find those solutions for those pieces themselves? We can utilize the quadratic formula to find the last two solutions. All right, therefore, x is equal to the opposite of negative 3. So the opposite of b plus or minus the square root of b squared minus 4 times our a value of 2 times our c value of negative 3 all over 2 times our a value of positive 2. This reduces then to positive 3 plus or minus the square root of 9 plus 24 over 4, or 3 plus or minus the square root of 33 over 4. Now when I look at the square root of 33, 33 is not divisible by any perfect square numbers. It's only divisible by 3 and 11. Both 3 and 11 are not perfect squares, so I'm not able to reduce this down any further. And notice it's in its exact form. Our three solutions then are x equals 1, that was given. We used x equals 1 to reduce the polynomial, so we could identify the other solutions. We then used the reduced polynomial to find the quadratic formula to find the other two solutions as 3 plus the square root of 33 over 4 and 3 minus the square root of 33 over 4, which you could utilize your calculator and find that the decimals match what we see in Desmos. Let's head to slide 4. We'll follow this same process again. We have 4x to the 4th minus 4x cubed minus 11x squared plus 12x minus 3. It's already written in descending order. we should have 4 solutions. It's telling us that given that 1/2 is a 0 of multiplicity 2, so we get to count 1/2 twice. So when I'm finding all of my solutions, x equals 1/2, we get to count that 2 times. Find the other 2 zeros. We do see that there are 2 additional zeros. And noticing that those 2 additional zeros are, again, ugly decimals, so there's probably going to be something weird and wonky. We're going to utilize synthetic division to find our reduced polynomial in order to find the other 2 solutions. But I'm going to do reducing the polynomial twice, once for each half. So I'm going to start with half on the outside. I know that is a solution. And then bring down my coefficients for -4, -11, 12, and -3. Always bring down 4, the first value. I'm going to then take 1/2 times 4, which is 2, so half of 4 is 2, and then add, so -4 plus 2 is -2. Half of -2 is -1. When I add together, we have -12. This is working out perfect. Half times -12, so half of -12 is -6. 12 minus 6 is 6. Half of 6 is 3. -3 plus 3 is 0. Should not surprise us that we have a remainder of 0 because we know that 1/2 is a 0. I now have a reduced polynomial. I'm going to do this again with my reduced polynomial. I'm going to use 1/2 and do this all over again to find another reduced polynomial. So where I left off using these values, we're going to do this again for -2, -12, and 6. Always bring down the first term. Half of 4 is +2. -2 and 2 is 0. Half of 0 is 0. -12 plus 0 is -12. And half of -12 is -6. So 6 and -6 is 0. Again, shouldn't surprise us because we knew that it had a multiplicity of 2, so it should divide into it 2 times. Again, we have a new reduced polynomial that we can use. That reduced polynomial has 0 x's, this is the x column, and x squared, and we could keep going if we desire. Notice that we started off with x to the 4th, and we took away 1 x for the half and another for the other half, so that is why I'm down to x squared, because I've divided out 2 x values. Now I have 4x squareds plus 0 x's minus 12. And now I can use this reduced polynomial, set it equal to 0, and find my other x's. I could add 12 to both sides, so 4x squared is equal to 12. X squared is equal to 3. And when I take the square root of both sides, x is equal to plus or minus the square root of 3 in its exact value. Therefore, my other 2 solutions are the positive square root of 3 and negative square root of 3, where if I were to plop them into my calculator, I would find that we would have -1.732 and positive 1.732, which match. We have found all 4 solutions. Let's do another example. Here I'm given the polynomial of x to the 5th plus 2x to the 4th minus 12x cubed minus 38x squared minus 37x minus 12. Given that we have a solution of -1 and it has a multiplicity of 3, so we get to count this 3 times, yay, what are the real zeros, the other real zeros. So I get to count this -1 solution 3 times. Therefore, x equals -1, -1, -1. I do see that I have 2 other solutions here that are nice whole numbers that thank goodness for decimals that we can utilize that to help us along. I could reduce my polynomial by dividing by -1 3 different times, and we'll do that so we can just kind of get practice. I'll start with -1. All right, we'll have 1x to the 5th, 2x to the 4th, -12x cubed, -38x squared, -37, and -12. Always bring down the first value and multiply. -1 times 1 is -1. 2 minus 1 is 1. We'll have the same result, except when I add -12 and -1, we have -13. -1 and -13 is +13. So when I add, I have -25. -1 times -25 is +25. So when I add, we have -12. We end up with +12 and a remainder of 0. Again, shouldn't surprise us. We know that it has a multiplicity of 3, so I can do this again. Using my reduced polynomial here, we can reduce it even further. Yes, I know we can visually see what they are, but just to kind of get an idea. Always bring down the 1. So -1 times 1, we end up with a 0. -1 times 0 is 0, so -13. +13 when we multiply, so -12 when we add, +12 and another 0. Again, shouldn't surprise us. We have another reduced polynomial that we will do this one more time, one for each time it's a solution. Always bring down the first value, so -1 times 1 is -1. When I add, -1 and -1 is +1. And here we go, +12. So we now have a reduced polynomial. 0 x's, x squared. These are the new coefficients. We have x squared minus 1x minus 12. We actually can factor what multiplies to -12 but yet adds to -1. -4 times +3. Our factored form then is x minus 4, x plus 3. When we set this equal to 0, x minus 4 is 0, x plus 3 is 0. Therefore, x is +4 and x is -3. So our solutions then certainly match what we see visually. There may be times, and we'll see this on the upcoming slides, that it's going to ask you to write the polynomial in factored form. It's going to write the polynomial in factored form. Well, I already have partial of it, x minus 4 and x plus 3, but I also have these values of -1. So right now I have x is equal to -1. Therefore, x plus 1 is 0. Notice how I'm kind of working my way backwards, and that there are 3 of these. So using my solutions, its factored form is x plus 1 cubed, since there are 3 x plus 1s. I also have x minus 4 and x plus 3. So I just wrote my polynomial in its fully factored form. On the next slide, I have another example of this on slide 6. Create a polynomial when I'm given the following characteristics. So it's telling us that the solutions are C are equal to 1 and C is equal to 3 with a multiplicity of 2. This tells me that X is equal to 1, X is equal to 3, and X gets to be equal to 3 twice. Work our way backwards. X minus 1 is 0, X minus 3 is 0. Putting it in then to our factored form, X minus 1, X minus 3. Working our way backwards from solving, we've done this many times going forward. And then it's asking us for the polynomial, so we need to actually multiply these out. Well, X minus 3 times X minus 3 is a difference of perfect squares here. So X minus 1 is, or X minus 3 times X minus 3 is X squared minus 6X plus 9. So using our ideals of what we know about polynomials to quickly multiply, and then ultimately distribute the binomial by the trinomial. So I'll distribute my X first to each item, gives us X cubed minus 6X squared plus 9X. Now we'll distribute the negative 1 minus X squared plus 6X minus 9. And then combining like terms, I have 1X cubed minus 7X squared plus 15X minus 9 on its own. So our polynomial function is X cubed minus 7X squared plus 15X minus 9. And our last example on slide 7. Here it's giving us some information. We need to have a degree of 4. We know that that means that there are 4 solutions. It tells us that it has exactly 3 x-intercepts. We also know that our x-intercepts are at -6, 1, and -117. So that's pretty interesting. We also know that it has a negative leading coefficient because as our x values go to positive infinity, our y values go to negative infinity. This gives us the negative leading coefficient. And that comes from Friday's lesson. We also know that it crosses through the x-axis at 1. So because it crosses through the x-axis at 1, this tells me that this has an odd exponent. So if we're thinking about x equals -6, x equals 1, and x equals -117, going backwards, we'll have x plus 6, x minus 1, and x plus 117. This tells me that this has to have an odd exponent, because if the next odd exponent was 3, we would have 3 solutions here, 1 here, and 1 here, but that would be a total of 5 solutions, and we know we only have 4. Therefore, either x plus 6 or x plus 17 has more than one solution included in it. I'm going to put it with the x plus 6 just because it has easier values to it than the x plus 17. So I'm also going to have this have one solution. So I've got 2 from the x plus 6, 1 from x minus 1 that was given, and then 1 plus x plus 17, so that I have a total of 4 solutions. And then, of course, we also know that we have -1 in the front because it has a negative leading coefficient given from the parameter here from part 1. Our next step then is to actually multiply all of these out. And I know you know how to multiply all of them out. So your ending polynomial has to be negative x to the 4th minus 128x cubed minus 1311x squared minus 2772x plus 4,212. Just to make sure I had it all correct, once I found my polynomial, I did insert it into Desmos here just to verify that all of the parts that were given to me actually came out okay when I actually graphed it, so that it matched the given parameters. Sometimes it's easier to visually see than it is to make sure visually just looking at the polynomial itself. So that's my hint, to utilize the graphing portion to help verify that as the algebra gets a little more intense, that you're able to find the solutions more efficiently, and then pair your algebra up with it.